Alright guys, so today we are going to start talking about how the atom is arranged. So in previous lessons, and especially before break, we talked about what an atom is, what matter is, and we've just kind of got the basics down so far. So just as a reminder, an atom we define as it's like the building block of matter. All matter is made up of atoms. And it's really kind of an abstract concept. It's this tiny, tiny little thing, and for a while people thought it was the smallest piece of matter. So what we look at today is how ideas about the atom have changed throughout history. So before we can do that, we need to define three terms that we've already talked about in this chapter, but now we're going to be accountable for a lot more about these three terms. So the first one is protons. Protons, we have said before, they're positively charged. Okay, so remember, protons start with P, positive starts with P. Now, a new component that we're going to talk about now is the location of these particles. So protons are smaller than atoms, which we're going to see throughout the lesson today. And so inside the atom, if we could zoom in the center, we now know there's this positively charged region in the middle called the nucleus. Now, if you think back to last year's science, we also defined the term nucleus. In life science, we said the nucleus was like the control center of a cell. It was right in the middle usually, and it was kind of the brain of eukaryotic cells. It was where the DNA was stored. This is a different definition of nucleus. Now we're looking at it from the physical science component, but it still has kind of a similar idea behind it. In physical science, the nucleus is the positive region in the middle of an atom, and that's where all the protons are found. So, protons are positively charged, and they are found inside the nucleus of atoms. Okay. The next term is neutrons. Okay, neutrons we said was a tricky one because it starts with N, so we tend to think negative. But remember that prefix neut? Neutrons are neutral. That means that they have no charge. They're not positive or negative. Neutrons are also found in the nucleus. And I mean, that seems to make sense because if they have no charge, they won't affect the positively charged nucleus. And the last type of these tiny little particles are electrons. And electrons, we've said before, are negatively charged. And that's going to be really important for the entire rest of the year. Electrons are kind of the odd particle out. They are the only subatomic particle found outside the nucleus. So that's kind of where we start today, is looking at how these three really important particles were discovered and the theories that led up to them. So, the first thing that you need to know about this chapter is that we are using models. Okay, the model that we're going to use primarily when we draw atoms is actually not the most accurate model. Okay, the theory of atoms has developed over the years. So we're going to look at how it developed, but each model does have somewhat of a flaw to it. And down here I made sure to put this in, it's very important. As we study these models, please remember, some of them are inaccurate. We're studying how this theory has developed. So the first few models, well, they're not all correct. That's why they had to be developed. So as we study them, please remember that some of them have incorrect information. Don't take all of these theories as fact. Okay. And there have been, so up here I put there's been 5 main atomic models. There have been many more, but these are the 5 that we kind of focus on this year. All right, the first scientist that we're going to look at was Democritus. Okay, so he was one of the early thinkers who really had a science focus. And again, just like when we studied cells and things last year, just because these 5 people are the ones we talk about this year does not mean that they were the only 5 to make discoveries. These are just the ones that most credit is given to, whether it's because they were more published or had more work that's been discovered. But Democritus is the one who was credited with proposing the idea of atoms themselves. So, based on his studying, he kind of came up with the idea that the smallest, if we were to take a piece of paper and tear it in half, and then tear the half in half, and keep going until we couldn't see it anymore, eventually we'll get to a point that is the atom. And that comes from, I believe it's the Greek, for indivisible. Okay? It can't get any smaller. So Democritus thought that atoms could not be broken down into anything smaller. Now we know that's not accurate. We know there's particles that make up atoms, but back then, I mean, this was still a huge, huge discovery. He said that an atom of iron would have the characteristics of iron. So it would be shiny, it would be strong, and that's what made iron have those characteristics. An atom of cheese, if we were to break it down all the way, has all of the characteristics of cheese. It's a silly example, but that kind of gets the point across that atoms were what gave things their characteristics. Now, quite a bit later, there was a scientist named John Dalton. Okay, and he actually had a lot of statements about the atom. We kind of summarize it in one sentence, but probably in high school you'll study John Dalton quite a bit more in detail. The key point for John Dalton, he said that atoms of an element are identical. And the other component, that different atoms combine to form compounds. So we've got some new vocab terms in here. The first one is element. Now we defined this before break, but just a reminder, we said that an element is a pure substance. It has a definite composition. So John Dalton said that every single atom of an element would be identical. So all hydrogen atoms are the same. All copper atoms are exactly the same, but they would be different from the hydrogen atoms. So that was his first major statement. The second one, he said that different atoms combine to form compounds. So again, we have to think back to before break. We said that compounds are also considered pure substances. The difference between a compound and an element, a compound is when we have at least two different types of elements that have chemically bonded together. They still have a definite composition. So the example that we gave was water. Water can be considered a compound. It has one oxygen atom and two hydrogen atoms. All water molecules will always have that exact composition, so it's a compound. So where John Dalton comes in, he said that these compounds are formed when different atoms bond together, which we would say is pretty accurate. We have oxygen and hydrogen in water. Those are different types of atoms. They've combined, and that makes a compound. So far we've covered Democritus and John Dalton. The next scientist who proposed a structure of the atom was J.J. Thomson. Now again, this was in more modern history. In Thomson's model, he said that there had to be some type of small negative particles. So he was the first one to really make the claim of charges in an atom. And the important component for Thomson, he said that those small negative particles were kind of stuck or embedded in a positive sphere. So this is great progress. This is the first person to really come up with the idea of charges in an atom. It's still not accurate though. So he would say if we have an atom, well, there's some positive stuff, and that's the whole thing is positive. But then inside of that, there's a couple of small, just negative particles. That would be Thomson's model. Again, progress, but still not completely accurate. A way of remembering Thomson's model is called the plum pudding model. Right now, in America, in modern day America, we don't really have plum pudding. But to me, you guys know that I am certainly fond of chocolate chip cookies. think of it, it could be called the chocolate chip cookie dough model. Okay, so I have a picture for you. So this right here is what plum pudding looks like. Okay, it's like a bread pudding, and it has plums in it, hence the name plum pudding. This over here is a diagram. So, like we saw on the last slide, in this diagram, that bluish color is just positive. So it's not particles, the whole atom is positive, but then each of these little negative dots would be particles that are just stuck in the positive. So in the plum pudding, the bread part itself would be positive, and each of the plums would be negative. Okay, so that's Thomson's plum pudding model. Now, on the diagram, we've kind of jumped ahead. Even though Thomson didn't use these terms originally, now those negative blobs, we call those electrons. So we could say that Thomson was really the first one to discover electrons. All right, next is Ernest Rutherford. Now, Rutherford had the next big step when it comes to the atom. He had the idea that instead of the entire atom being positive, there was a positive charge in the middle, in the center, which we now know would be the nucleus. So Thomson discovered the idea of electrons, and Rutherford came up with the idea of the nucleus, which kind of led to protons. And on the next picture, I'll show you how he discovered that. He came up with this experiment, and he actually used charged particles to test and see if there was a charged region in an atom. So again, Rutherford's big thing was positive charge, which we now know would be considered the nucleus of the atom. And again, he was the one who was credited with saying it's in the center. So that's a really big step. And before I show you the picture of that, the scientist afterwards is Niels Bohr. So if you've heard of a Bohr model of the atom, that's who we're talking about. The Bohr model says that electrons, those negative particles that Thomson came up with, they travel in orbits, or think circles. Think of how a planet orbits the sun. So these electrons orbit around the nucleus, and they only change orbits when the energy is added or removed. That's a lot of information, and that was a huge leap. Now, this, we could say, is fairly accurate. The Bohr model is actually the model that we use when we draw atoms in class. It's still missing a crucial detail, but this was pretty big. So Bohr took Rutherford's concept of the nucleus. So in the center of an atom is this positive region. What Bohr said is there were these almost like rings, which he called orbits. And these rings are around the nucleus, and they go all the way around it. And that's where the electrons live. Okay, so maybe there's some electrons on this ring, there might be some on this ring, and the electrons are always going to be on one of these rings or orbits. That would be the Bohr model. Okay. Now, the second part of that says electrons can only change orbits when energy is added or removed. So all that means is if this electron wants to get to this energy level, we would have to add some energy to it. And later in the chapter we'll talk about that would excite the electron so it's able to jump up the energy level. That's a lot of information. For now, for this portion of the chapter, all you need to know is the Bohr model has electrons traveling in orbits. Okay, the rest we'll get to in a little while, but the important part of the Bohr model is the electrons are in those orbits. So here are some pictures for, well, let's see. We need to figure out if this is the Rutherford model or the Bohr model. So when I look at this first picture up here in the top corner, I see a positive nucleus in the middle and negative electrons, but they're kind of just free floating. The fact that they aren't in those orbits tells me this is the Rutherford model. It has a positive nucleus in the middle, and the negative electrons are just floating around it. So this would be Rutherford's model of the atom. Now, the way that he did this, and you won't need to know this year, I just think it's very interesting. Rutherford set up an experiment, and he had this radioactive source. Now, he had it in a box, and he set it up so that it would send out or emit these things called alpha particles. Now, alpha particles have a positive charge. They're just positively charged particles, similar to a proton. What he did, he had this piece of gold foil. And around the gold foil, when we see where it says fluorescent screen, he set up this screen that would actually indicate when it was hit by charged particles. It would give off light. So he could tell where the alpha particles were hitting the paper after they went through the gold foil. So if we look at the diagram, we see that all of the alpha particles leave in a straight line. And it looks like most of them keep going straight through. It's almost like they hit nothing. But some of them came off at an angle, and one or two even bounced backwards. So based on what we know about charges, like charges repel. Think about a magnet. The North Pole and the North Pole repel each other. They have the same, we'd think of it as like a charge. Electricity works the same way. So Rutherford said, well, these alpha particles were positive. So there must be something positive in the gold paper that caused those alpha particles to bounce backwards. But most of them went through. So if we look back at our model over here, that's why he said the nucleus had to be in the center. But looking at the size of the atom and the size of the nucleus, Rutherford said that most of the atom was actually empty space. That's why so many alpha particles went straight through. Look at all the white space in our atom. So alpha particles could travel straight through that, whereas the ones that hit the nucleus, well, they were prevented from actually hitting it. It was the same charge, so they were bounced right back. That's Rutherford's experiment. Now, if we look at this model, let's see. I see something in the center, and it has some positive particles, and then some particles that look like they have no charge. And that's in the middle. And then around it, I see rings with negative charges on it. So based on that, which model do we think this would be? Well, the only model we've talked about so far with rings is the Bohr model. So this would be our Bohr model. Now, this built off of the idea of the nucleus, and this even has in those neutral particles, the neutrons. But we can see the electrons are clearly found on those orbitals, those rings. Okay, now if we look at the bottom diagram, eventually this year, we'll talk about how we can figure out how many electrons are able to fit on each energy level. So on this diagram it tells us on the first level we can fit 2 electrons. The second level we can fit 8. On the third level we can fit 18. By the end of the year, you're going to be confident about knowing how many can fit where. And that's what determines chemical bonding. I know everyone is excited to see all sorts of chemical reactions and all these chemical changes. Well, the reason for chemical bonds and the reason we can have those great reactions is all because of how these electrons are arranged on the energy levels. All right, the last model that we're going to talk about wasn't really published or announced until 1926. So really, in the grand scheme of things, that's not that old. So this is called the electron cloud model. And currently, this is the closest thing to the model that scientists use today. Now, the electron cloud model, the name kind of gives it away. It says electrons are found somewhere in a theoretical cloud. And all that is it's an area somewhere around the nucleus. This is a really vague model, and it's not one that we can really draw, which is why in class we use the Bohr model to draw atoms. The reason they have this theoretical cloud of electrons is because the electrons are so small. And because they're so small, they're moving really fast. So because they're so small and so fast, statistically, it's pretty much impossible to know the exact location of an electron. So what this model does is it will actually shade in regions around the atom where there's a probable chance of the electrons being found. It gets really, really complicated really fast. So this year, all you're going to have to know is if I were to give you the definition or describe the model, you'll just have to remember that this is the electron cloud model. If we were to have some type of picture, so this one is a very simplified diagram. This would be something you'd find in a textbook. So it still has a nucleus, and then rather than those really clear-cut rings going around it, it has just kind of shaded regions. So somewhere in this kind of vague cloud, there's probably going to be some electrons. And then again in this one around it here. But very vague. Now if we look over at this diagram, this one, they use dots. And so you can see some of the dots are very faint, some are darker. So they're actually, and there's a very, very complicated way to calculate the possibility of electrons being in certain locations based on how many electrons can be in that range and how close they are to the nucleus. So other than recognizing what the electron cloud model is, you won't have to do any drawing of this or recognize an atom with the electron cloud model. Right. So if we were to summarize, we had 5 models today. The first model was Democritus's model. Now, Democritus's model, he just stated that there was an atom. So no drawing really associated. He said that an atom was the small particle that made up matter, and we couldn't get any smaller than an atom. Our second model was Dalton's model. And again, with Dalton's model, there wasn't really an image, but he was the one who really started to advocate for the idea of elements and compounds. That all elements have identical atoms, all elements have identical atoms, and compounds were made out of different types of atoms coming together. Our next model we talked about was Thomson's model, and that was our plum pudding model. So Thomson said that an atom was made of a positive substance, and there were negative particles stuck in the positive substance. So that's where we came up with the idea of electrons. Our fourth model was by Rutherford, and that was where he came up with the idea of the nucleus. Using his gold foil experiment, he said that all atoms had a positive region in the middle, which we now call the nucleus, and then most of the rest of the atom was empty space, but there was some negative stuff floating around too. And the fifth model we looked at was the Bohr model, and that's the model that we will use to draw atoms in class. Bohr added the idea that those negative electrons traveled around the nucleus in circular orbits, and they had to stay on those orbits unless they gained or lost energy. And then the last kind of extra model that we talked about was the electron cloud model, which we said is a difficult concept to understand, which is why we just kind of define it this year. And the electron cloud model just said that we really can't know exactly the spot where an electron would be. So there are these clouds of probability where they could be. So hopefully this made some sense for you. We will go over it again throughout the chapter, but it's essential to know kind of where the thought of the atom came from and what we think now. Because atoms are how we talk about, chemical bonding, chemical reactions. It won't make sense unless you understand how the atom is set up. All right, thanks everybody.